This is section 11.4, series and sigma notation. Just a note, you are going to be totally lost if you haven't completed the introductory activity that we did in class together. It's pretty self-explanatory, so if you missed it in class, please go back to the blog, download that from our Google Documents page, and then you can come back and finish the video. So you're already really familiar with sequences. When the terms of a sequence are added together, what's resulting is called a series. Let's take this example. Here's a sequence that you should be fairly familiar with. It's an easy arithmetic one. And then for a series, all you're going to do is take those same terms and add them up. So 2 plus 5 plus 8 plus 11 is the series related to that sequence. So we've explored sigma notation together a little bit, but just a reminder of what's happening here. N equals 1, that tells you where to start. That's the first number we're going to put into the formula on the right. And 50 tells us where to stop. We'll put in all of the natural numbers between 1 and 50. So it looks like this: 2 times 1, 2 times 2, 2 times 3. We'll put a dot, dot, dot because we don't really want to write all those terms. And then it'll end with 2 times 49 and 2 times 50. That notation's a little messy, so we're going to simplify each term without actually adding them all together. That's called expanded form when it looks like this. And then, of course, you could find the actual sum, which is 2,550. We'll talk about how to do that in a later section. All right, so this is just asking us for expanded form. We're going to start with 4 and end with 7 and put each of those numbers individually. So we have 3 times 4 minus 2, plus 3 times 5 minus 2, plus 3 times 6 minus 2, plus 3 times 7 minus 2. That's not expanded form yet because we haven't simplified those. We just put the numbers in the right places. 3 times 4 minus 2 is 10. Then we get 13, 16, and 19. So that's expanded form. Expanded form again, just a little bit more complicated because there are exponents, but we'll start with 1 and end with 4. The parentheses in this particular problem are really, really important because you want to know that you're taking negative 2 to that power, not just 2 to that power and then making the answer negative. The order of operations there is really important. Because a negative to an even power is positive, but a negative to an odd power is negative. So you'll see we have some alternating things happening here. So I get negative 2 to the second, which is positive 4, and then I get negative 2 to the third, which is negative 8, negative 2 to the fourth is positive 16, and negative 2 to the fifth is negative 32. Again, that's expanded form. We don't actually have to add those together for expanded form. All right, and now we're going to work backward, going from expanded form to sigma notation. The first thing we're interested in is what kind of series is this? Just like we have arithmetic and geometric sequences, we have arithmetic and geometric series. Because to get from one term to the next in this, you add the same thing. This is an arithmetic series, which is really nice because we already know some things about arithmetic sequences and series. I can write a formula for each term of this series, and that's just that the nth term is equal to the first term plus the common difference times n minus 1. In order to use this in sigma notation, you'll want to simplify it. So we get 5 plus 5n minus 5, which just simplifies to 5n. So that's the formula you'll put on the right side of your big sigma. So here's my capital sigma, and I know that 5n goes on the right side because that gives me every individual term. I know this because it's going to start with n equals 1, and then the question is, how far do I go? Which term of the sequence is that? Well, you can set that equal to the formula we just found and solve it for n, because remember, n tells you where you are. Dividing both sides by 5, we get n equals 50, so I'm going to add up from 1 to 50 of 5n. Fortunately for some series, the formula is fairly obvious. That's 3 times 4 to the first, plus 3 times 4 to the second, plus 3 times 4 to the third. Notice that the exponent matches what term we're on. The first term has a power of 1, the third term has a power of 3. So in general, the nth term will have a power of n. T sub n equals 3 times 4 to the nth power. For sigma notation, we need to know where we start and where we finish. Notice that the first term has a power of 1, and the last term has a power of 24. So that means we're going to add up from the first term to the 24th term. Whoops, you don't need an n equals on the top there, my mistake. And it'll be 3 times 4 to the n. This example is going to be very similar to one we've already done. The first thing we're wondering is what kind of series this is. And if you take a look at the series, you'll notice that you're adding 4 every time to get to the next term. so it must be arithmetic. Here, I'd like you to pause it and try this one on your own. It's very much like the example, not the one we just did, but the one right before it. I won't talk through this one, so just follow it on your own. Remember that here you're going to solve for n because n tells you where you are in a sequence or series. It talks about the position of a particular term. Another one where the formula should be fairly obvious. Notice that underneath the radical we have multiples of 7. 7 times 1, 7 times 2, 7 times 3. So that'll give us an idea for the formula. If the first term is 7 times 1, the second term is 7 times 2, then each consecutive term, the nth term, is 7 times n. Wherever you are, 7 times that number will give you the term in the sequence. So that last term then, because it's 7 times 11, must be the 11th term in this series. So we know where to start and where to end with our sigma notation. We'll start with n equals 1, go up to 11, and the formula for each particular term is radical 7n. Here's one where the formula might not be so obvious. So again, we're going to ask ourselves, what kind of series are we looking at? It doesn't look arithmetic because if it were, you'd be subtracting or adding the same thing every time. But if you multiply each term by negative 1/2, you will get to the next term. So it looks like this is a geometric series. Because this is geometric, thanks to section 11.3, you know how to write a formula for each term. The nth term is equal to the first term times the common ratio to the n minus 1 power. And now we'll put that into sigma notation. The formula goes on the right-hand side. Since 8 is the first term, we know that we'll start with 1, and because this is an infinite series, it goes on forever, we'll end with infinity. Here's another series to write in sigma notation, and again, we're going to start by asking ourselves, what kind of series is this? If it were arithmetic, you'd be subtracting or adding the same thing every time. To get from 1 to negative 1/3, you would subtract 1 1/3, and it doesn't look like that'll get you to 1/5. So this isn't arithmetic. Similarly, to get from 1 to negative 1/3 by multiplying, you would multiply by negative 1/3, and again, that won't get you to 1/5. So this is not geometric either. Instead, because this is a fraction, we're going to look at the top and the bottom of the fraction separately and see if they follow any kind of pattern. The top looks to just be ones that alternate positive and negative. And the nice thing about that is, you know, if you have a negative number and you take it to an even power, you get a positive number. And if you have a negative and you take it to an odd power, you get a negative number. So then we need a formula that will give me even for the first power and odd for the second power. Since the first number you plug in is 1, if I add a 1 to that, I get 2, which is even. So that takes care of the first term. And then if I add a 2 to that, I get 3, which is odd, which takes care of the second term. So negative 1 to the n plus 1 power will do it. Generally, if you have something that alternates negative and positive, you can either use negative 1 to the nth power or negative 1 to the n plus 1 power. If you really like geometric sequences, you can think of this as geometric as well, with a first term of 1 and a common ratio of negative 1. And so you would do negative 1 to the n minus 1 power, which would accomplish the same thing. The nice thing about this is that the denominators of these fractions, the bottom of our series, is a really beautiful arithmetic sequence, a really simple one to write a formula for. 1, 3, 5, 7. You'll notice that to get from 1 to 3, you add 2. From 3 to 5, you add 2. So this is clearly arithmetic. And we can write a formula for each term. The nth term is equal to the first term, which is 1, plus the common difference of 2 times n minus 1. And we can simplify that to 2n minus 1. So put all that together, you have a formula for the entire thing. We have a sequence that goes from 1 to infinity. The top part of that formula is -1 to the n plus 1, and the bottom part is 2n minus 1. Never fear, this is the most complicated kind of series you'll see in Algebra 2. And lastly, a problem word problem style. We want the series consisting of positive two-digit integers that end in 2. Well, my first positive two-digit integer ending in 2 is 12. The next is 22, then 32, and the last one that only has 2 digits is 92. So that's my series. And once you have it written out, it's pretty simple. This is clearly an arithmetic series with a common difference of 10. So writing a formula for each term of the series is pretty simple. The nth term is equal to the first term plus the common difference times n minus 1. You can simplify that to 12 plus 10n minus 10, which is 10n plus 2. So that's the formula that will go to the right of our sigma. 12 is the first term, and it might be obvious to you which term 92 is, but in case it isn't, remember that you can always put 92 into our formula and solve for n, which is its position. N is where you are in the sequence. Since n is 9, 92 is the 9th term of this series. So our sigma will start with 1, end with 9, and the formula for it is 10n plus 2.